G'day kids, how you doing? This is the Barker past paper we've been doing. We're up to question 15C now, so we're very hot towards the end of things. Things are really heating up. And this is a question to do with differentiation and how when you differentiate displacement with respect to time, you get velocity and a few other really spicy little ideas are in here. So Lee rolls a marble. So your mate Lee is rolling marbles, right? And so the distance x. What it is after he rolls the marble, it's moving away from him. And the distance x is, at any given point in time, x is how far away that marble is away from, where Lee started rolling it. So we've got this equation here, and you can see it's x is how far the marble is away from Lee at any given point in time. So we chuck a time in here into the right-hand side, and then we're going to get a number out, and that's going to be how far the marble is away from Lee. But you can see it says 0 is less than t, which is less than or equal to 3. So what that means is we only consider the first 3 seconds, right? So Lee's going to roll this little marble of ours, and then we only want the first 3 seconds of action. Whatever happens after then, don't even think about it. Cool. So the first question is sketch the curve of this function. Cool. So I'm sorry guys, I've started on it a bit just to make it a bit more exciting learning for you guys rather than watching me draw out stuff. So I've just rewritten the equation here. So x equals 4t squared minus t cubed. Too easy. So this is the displacement function, and you can tell it's a function of time. So what I've done initially, we're going to find the roots or where it cuts the x-axis. Well, the x-axis is a bit tricky here. I shouldn't say that because on the vertical axis here we've got displacement, and usually it's y, but we've put x here. So that's don't be too worried about that. It's just a bit confusing. So displacement is on the y-axis, what used to be the y-axis, and on the horizontal axis we've got time. Beautiful. So when we factorize this, we take a t squared out, and then when we expand this out, we're just going to get 4t squared, which is what we're at the top, minus t cubed. Beautiful. So when x equals 0, so when it's at the starting point, where he starts rolling it, 0 equals what we've had just up here. And so what we're going to do is we're going to get a repeated root for t equals 0. So of course when time equals 0, it's got no displacement because it's still in his hand. But also you can see when t equals 4, if I've got a 4 here, we're going to get 4 minus 4, this is going to be 0. So at t equals 4, there's also going to be a point where it cuts the horizontal axis. But we're not so much interested in this 4 here because we know it. We're only interested in the first 3 seconds. So I've just put it here, but don't really need to worry about it. Too easy. So the second part, what I've done is I want to find out, just so we can draw this graph, when t equals 3, how far is it away? So here's the equation of displacement with respect to time. So I've just chucked t equals 3 into here. So we put 3 into there, we're going to get 9. I've actually done it here. So 4 times 9. And then when we put 3 into here, it's 3 cubed, which is 27. Cool. So this is all when t equals 3. So we've got 36, 4 nines are 36, minus 27, so that gives us 9. So when t equals 3, x equals 9. So I've just done that here. So t equals 3, x equals 9. So this is going to be a point on our graph just there, as well as the starting point of the origin. Too easy. So now what we're going to do is we're going to see, so remember it says showing any stationary points. So stationary points are points where the gradients are flat. So we're going to differentiate this displacement function to find the gradient function, or the first derivative. And if you haven't seen this before, if we're differentiating a displacement with respect to time, what we end up is with velocity. So you mightn't first realize, but say you've got some graph here. And so this is displacement and this is time. So, and there might be in meters here and in seconds here. So you got some graph. The gradient at some point, what are the units of that gradient going to be? Well, gradient is grad. So that is rise over run, isn't it? So our rise units will be in meters, and our run units will be in seconds. So meters per second, that's like, that's a speed, isn't it? Like, or say this was in kilometers, right? And this was in hours. Your gradient would be in kilometers per hour. So obviously the gradient is the speed, because kilometers per hour is the thing that's on your dashboard in your car. So the gradient represents velocity when you're dealing with a graph with displacement on the vertical axis and time on the horizontal one. So we're going to differentiate to find the gradient function or the velocity function. So what I've done there was, so the 2 comes down, 2 times 4 is 8, and then we drop the power by 1, so now we've got a 1 here. And then the 3 comes down the front here, and then we drop the power by 1, so we just get t squared. Hopefully there's no quarrels on how to differentiate. So now we're just going to, we're going to factorize this, so I'm just going to take a nifty little t out. We're going to get 8 minus 3t. Cool. So I'll say, so when x dashed of t equals 0, so that's when we're going to have equals 0. So that's when the gradient is flat. So I'll say I dot e when the gradient is flat. So I'll say when m is flat. Cool. So then we're going to have 0 equals, so we've just put a 0 in here, and we're going to get t over 8 minus 3t. Juicy. So t will equal 0, or t, or this part here will equal 0. So we're going to get 8, well, if this 8 minus 3t equals 0, then we're going to have, of course, 3t equals 8, t equals 8 on 3. Beautiful. So these are when the gradient's at flat. So it's flat at this point here. So I'm going to write flat here. Beautiful. So that's at that point when t equals 0. And also at this point we're 8 on 3. So what is 8 on 3? That's 2 2/3. So that is a little bit under 3, isn't it? So we do have to worry about that. So I'm going to pop that here. So I'll do a red. So at 2 2/3. Cool. That's where we're going to have a stationary point. So now I want to know at what y value is this stationary point? You know, how far away is it when the velocity is 0, or alternatively when the gradient is flat? Well, so here's our function that deals with displacement. So you got to be very careful what function you're using. This is your gradient function or your velocity function. This here in pink is the displacement. So if we want to chuck in 8 on 3. So I'll write x of 8 on 3. So that's saying when the time is 8 on 3, we're going to get 4 times 8 on 3 all squared minus 8 on 3 all cubed. And I just bang this into your calculator. So 8 on 3 squared times 4 minus in brackets 8 on 3 all cubed. And what do we end up with? I've just written it down here somewhere. So it equals something approximately equal to 9.48. Cool. So approximately equals 9.48. So that's a bit higher than at 3 here, isn't it? So it's going to be about, say here, I'm not going to do my diagram perfectly to scale. So if I say, let's do a cheeky pink, 9.48. Beauty. That's at this point here. So we're going to have a flat gradient here as well. Cool. So what's this graph going to look like? It's flat here. So the gradient is flat. Do it in green. So it's going to be like something very close to flat just here. Then it goes through this point. It's got to be flat there again, and it's going to finish just there. Cool. So obviously it's going to be something like this. Cool. So that incorporates everything we know. We know it goes through this point here, and it's flat. We know it goes through this point here, which is 2 2/3, 9.48, and it's flat. So we've got a turning point there. And then we know it finishes at this point here when t equals 3, and that's 9 meters away. When Lee rolls it, she finishes at 3 seconds. It's 9 meters away. Juicy. So we've sketched that curve showing any stationary points. We showed a stationary point there. Maybe I'd be really blatant and show that that's a flat point just there. Cool. So at what time? So that's the first part done. Too easy. 3 marks. Thanks for coming. All right. At what time is the marble furthest from Lee? So this is displacement. So where is it the furthest away? Well, obviously at this point here, because here it's 9.48 meters away and it never gets higher than that. So at what time is the marble furthest away? So the answer for 2 is at 2 2/3 seconds. Beautiful. Oh, also, just as a subtopic, I printed this off earlier. So this was done in Excel. So this is just to show that I'm just checking my answers here. So, it's at 9 at t equals 3, and it's a little bit higher than that here. So this would be about 9.48. We just worked out 9.48. Cool. And you can tell that the gradient's flat here at 0. And this cheeky little number down here would be, what was it? 2 2/3. 2 2/3. Beautiful. So we know, all right, Excel backs us up. Now, this third part, when is the distance of the marble from Lee increasing most rapidly? So increasing most rapidly, that's velocity. So when it's moving the fastest away, that's when its distance is moving away the fastest. And we know that the gradient of this curve, well, I'll do this one down here because this graph's a bit neater. The gradient of this curve represents the velocity. So so gradient represents velocity. So another way of saying when is it moving away the most fastest, is that most rapidly, is to say when is it moving away the quickest, when is it its highest velocity, when is the gradient the highest, right? That's another way of thinking about it. All right, so our gradient function was this, so I'll just write that down. So 8t minus 3t squared. So x dashed of t, that's a gradient, equals, what was it, 8t minus 3t squared? Yep. 8t minus 3t squared. So that's a velocity function. Cool. So when is the velocity the highest, right? So now we want to work out the function, which will be the acceleration that maximizes this velocity. So, all right, so when is the velocity the highest? So what we're going to do is we're going to differentiate again. So we're going to differentiate again, right, and to work out. So now let's just pretend this is the function velocity, and we want to know what maximizes the velocity. So we do the usual thing. We differentiate it once more. So we're going to get 8 minus 6t. Cool. And we want to know, so if we make that equal to 0, that will be, at which point is this maximized, the velocity maximized? So we'll say 8 equals 6t, because I've just plus 6t to both sides there. Cool. So t equals 8 on 6, which is 4 on 3 seconds. Beautiful. So at this time, at t equals 4 on 3, which is, 1 and 1/3 seconds, that's this point here. So 1 and 1/3, so it's about here. So that corresponds to the point where you can see here that I'll do a different color, that the gradient here is the steepest. Look, like here the gradient's really flat. Here the gradient's, flat. At this point here, the gradient's the steepest. So the velocity is the steepest. So the rate that it's moving away is the most. So it's at this time here, 1 and 1/3. Beautiful. So is that what they want to say? So but they don't know at what time. They want to know at what distance is the marble increasing away the most rapidly. So this is our function here, x, a displacement function. So I'll just write x equals, now what was that initial displacement function? Sorry about all this scrolling. It's 4t squared minus t cubed. Beautiful. 4t squared minus t cubed. Cool. So now we're just going to say, I'm going to write x of 4/3. So that's, 1 and 1/3 over here. So no tick, that's this part. So we're going to get 4 over, so we're going to get 16 on 9. Cool, so that's just t squared, 4 on 3 squared, minus, now what is 4 cubed? So it's going to be 16 times 4, which is going to be 64, all over 3. So 3 cubed is going to be 27. Cool. Now I'm just going to punch this into a calculator. Right, and so that will come to, what have we got? We've got, Pen tool's not working, 128 over 27. So that in Roman Catholic is approximately 4.74. So you can see at this point that corresponds to the graph, doesn't it? Because so there's this point of inflection, or the point where the gradient is the steepest. At this point here, 4.74 roughly meters. Beautiful. Okay. Well, yeah, that's everything. So that was a 2 marker there, and we had a 1 mark for this 2.23 seconds as the timer was the furthest away. So I hope that was clear, guys. I'll see you in the next vid. We're nearly done. I think we're on the last question now. Hoorah.